All right.
So it's my pleasure to introduce Martin Hils. He will talk about imaginaries in separably closed value fields.
Thank you very much for the invitation. It's a pleasure to be here. It's my first time in New York mathematically, and the only other time was 25 years ago for 2 days. So it's the first time then. Yeah, so this is joint work with Moshe Kamensky and Sylvain Rideau. It's basically model theory, but see, it has some connection to the topic of the general topic of the seminar, which I will make strong at the beginning. So what this talk is about, so we are interested in this valued field, say, so separable closure of Fp of t with the t-adic valuation, or the extension of the t-adic valuation to the separable closure. At the level of, well, imaginaries, this is the main point, but also to develop tools for the model theoretic study of such fields which go beyond axiomatization, quantified elimination. And the next level, I would say, in model theory is to know the imaginaries, and that is the main topic of this talk. So, okay, we'll start with a little introduction, and then we have 2 bricks to remind somehow separably closed fields without valuation, so just model theory is very well understood for a long time. I will be rather brief because maybe people are more or less familiar with the objects. And then from the valued side, the theory of algebraically closed valued fields. And then we combine the two and we'll be able to classify the imaginaries in separably closed valued fields using what was known as algebraically closed valued fields. Okay. So first, as a slogan, maybe, if you want to understand a framework, a model theoretic framework, say a theory or a structure very well, you also want to understand the definable quotients, like in any category. And definable quotient, so a definable set modulo a definable equivalence relation is called an imaginary. We'll talk about it second. And it's crucial if you want to understand, for example, definable groups. Many constructions go through imaginaries, and if you want to concretely get answers to questions, then you are in much better shape when you know, when you have a classification of imaginaries, or when you even eliminate them. We define this. Okay. So, what is an imaginary sort in a structure M? So it's just of the form D mod E, where D is a, well, let's take now zero definable. So D is zero definable set, no parameters involved, and E is a zero definable equivalence relation on D. Okay. And an element of such an imaginary sort is called an imaginary element of the structure. So an equivalence class for some definable equivalence relation. And we say that the complete theory eliminates imaginaries if for any imaginary alpha, say A bar modulo E in a model, there is a tuple which we could call a real tuple because it's actual elements, B bar, which is interdefinable with alpha. What does that mean? If you work in a sufficiently saturated model, this means that the class is preserved by an automorphism of the structure, if and only if the tuple is preserved by the automorphism. Then the two are interdefinable model theoretically, if you have this test in a sufficiently saturated model. Okay? That is elimination of imaginaries. Because then you can at least element by element replace the imaginary by a real tuple. Okay. Now remark, there is a canonical way, canonical construction due to Schellach, like tautological construction if you want. You just add all the imaginary sorts. You have a framework with many sorted structures, and then you get a theory in a canonical way, TEQ, which eliminates imaginaries, and you move also in a very canonical way from M to NEQ. And you do somehow what you expect. You just add them, and you have, it's like closing off a category under quotients. If you don't have them, well, you want to work with them, so you just work with them. Okay? Not, of course, in practice, it's not, it's sometimes useful in proof, but it's, in a complete situation, it is not enough. Yeah? And an important feature of the imaginaries is also if you eliminate them, then a definable set has a code. Does it mean? So you find a tuple, which usually is denoted by this code of D, so that the set, the definable set, is preserved set-wise by an automorphism if and only if the tuple is preserved point-wise. It's just you take a canonical parameter in a definable family, and the equivalence relation of defining the same set is eliminated, and that will be the code. Okay. That's useful, because you can talk about definable set somehow. Yeah? Maybe you have germs of functions and you want to talk about them, and then using the code you have a canonical object for this. Okay? And in the theory of fields, or more generally in the theory where you have two different constants which are definable over the empty set 0 and 1, for example, in fields, in the theory of fields, you have elimination of imaginaries if and only if an imaginary sort d mod E in a model can be definably embedded. So you find a zero-definable function on D going to some m to the m, so that it induces this injection. So in that sense, you can embed your imaginary sort into a real sort. Like it's just compactness plus the possibility of choosing. That's why you need two constants to do this. This is of course another view, but it's using compactness. It's not far from this definition, and in fields it's the same. So some examples. Okay, I mean there are of course many quotients. Let's look just at one very easy example. So take a zero-definable group action G on X, and then the set of orbits is of course the orbit equivalence relation is definable now, and everything is over the empty set, so you get an imaginary sort, the set of orbits. For example, if you take very simple, if you take a field, you take k squared, and you take the equivalence relation which comes from the action of Z2 permuting the two coordinates, then of course you can eliminate it because you have symmetric functions in fields. So you x y goes to x plus y, x times y. This eliminates exactly this. Up to permutation, understanding two tuples up to permutation is just you understanding the symmetric functions. But the same then works. Every finite imaginary in any field can be eliminated in a similar fashion, also on tuples using polynomials. I mean, it's not difficult, but this is somehow the baby case. Okay, in a valued field, this will be something we are interested in today. There are interesting imaginaries around. So the first ones, I mean, the residual field, so the ring of integers in your valued field modulo the maximal ideal is an imaginary sort, and similarly the value group, when you take the multiplicative group of the field and you quotient out by the multiplicative group of the ring of integers, you get the value group. So they're both imaginaries. Okay. Now, many theories, and you probably know this, I don't know, in this seminar maybe people talked about this, I suppose, but many theories of enriched fields do eliminate imaginaries. Poisson, who introduced the definition, showed immediately that algebraically closed fields eliminate. Real closed fields and also every O-minimal extension of real closed fields eliminate imaginaries by completely different proof. There's even definable choice. Differentially closed fields in characteristic 0, as you very well know, probably eliminate imaginaries. So you can, in the category of different constructible sets, say, you can go to quotients. Not preserving topology, but constructible category you can. Also Poisson. And then another argument yields it in ACVF. So if you take any completion of the theory of existentially closed difference fields, you also have elimination of imaginaries. That requires some higher amalgamation. That is another story, because here you don't have quantified elimination. Whereas in 1 and 3, it's basically quantified elimination of the theories, plus the fact, I write it here, plus the fact that you have fields of definitions for polynomial ideals. And the two facts combined give you this. Of course, in ACVA this does not work, because ACVA does not eliminate quantifiers, so you cannot reduce to ideals. You also have information to keep, which is of another kind, so that's why it's not formal. You need to do something else. Okay, good. That is some background about imaginaries. Now some about valued differential fields. So it's not really the motivation. It's the motivation to give this talk in this seminar, maybe. But it's also a disclaimer, because some of the connection is not so strong. So let's look at this. What is a valued differential field? Here you have a field which is at the same time a differential field and a valued field. And various of these have to be considered in model theories. Now, the following examples will all be in equicharacteristic 0. So Rosenlicht, for example, called it differential evaluations. What does he require? That the field of constants is trivially valued, that the ring of integers is equal to constants plus maximal ideal, and an abstract version of L'Hopital's rule. So if you have an element A which is of positive valuation and B of valuation bigger or equal to valuation of A, then A over B minus A prime over B prime must be of positive valuation, i.e. In the maximal ideal. And this is an abstract setting for the natural valuation you get on a Hardy field. But then it satisfies these conditions with the reals, the constants. And there, the model theoretic understanding of such valued fields with variations is a very important bit in Aschenbrenner van der Hoeven's work on the field of transeals. Like this, at the variational core, you have to understand these axioms and get information about it. Now another context is valued fields with a contractive derivation. So you require that the valuation of D of A is bigger or equal to the valuation of A. Scanlon studied these in his PhD thesis, and he exhibited the model showed that the model companion exists, VDF. And in a model of this model companion, one has that the residue field, first of all, the derivation induces a derivation on the residue field, which follows from contractivity, and the residue field will be differentially closed. And every value will be represented by a constant. So will be the value of a constant. This is gamma k is equal to gamma c. But very different from the first, because here the constants are trivially valued here. They give rise to all the values. Yeah. And also the residue field has a lot of, it's differentially closed here. It's a constant field, so it's very opposite. And now a last context, we show, he studied the model companion of valued differential fields where you don't impose any interaction on, so valuation and derivation can do whatever they want. Of course, arguably this is the least interesting case, but nevertheless, what I will talk about today, with the use of fuzzy derivations in separately closed valued fields, it is closer to the last framework. Because also we will not impose an axiom which describes or restricts the interaction between the valuation and the derivation later on.
I have a question. So in that condition of that Tom studied, so
yeah.
What would be a natural example?
Yeah, so you can take a different take a differentially closed field. Now take for example this. So you take Hans series field. Maybe write it like this. And now you take derivation coefficient by coefficient.
I see.
For example.
And valuation with respect to powers of t.
With respect to, yes, so exponents. So derivation component-wise derivation. It is a natural structure.
Would it be the equality in this case?
What will be the?
The equality, like variation of derivative would be equal to. No, we might have
You
constants.
see, because then you have constants, so that's why you have C of course, you have C of inside, so that you see that you get the full value group and so on. And it is very nice model theoretically, this structure, yeah? Of NIP and you know it very well. Okay. Good. Okay. So now let's start with the background. So I will first talk about separately closed fields without valuation, just to set some notation also and some results on imaginaries as well. So from now on, fields will be of characteristic P for some fixed prime P positive. Just notation, so K to the P to the N will be the set of elements which are themselves of the form X to the P to the N for X an element of the field, so it's a subfield, and Kp infinity is the intersection of all these. It is the largest perfect subfield of K. This one, by construction. Okay. For B a tuple from the field, and mu a function from the index set to the set from 0 to p minus 1 of finite support, we set b to the mu equal to the product in the obvious sense. Okay. B to the mu is product of bj to the mu j. It makes sense because it was finite support. Okay. And now B is said to be a p-basis of k if the b to the mu's form a linear basis of k over k to the p. So we are in the realm of p-dependence, p-basis. I suppose you are familiar with this, of course. So a p-base always exists, and any two p-bases have the same cardinality, E, which is called the imperfection degree. So somehow you have a notion of, you have a matrix coming from p-dependence, and you have everything basis, dependence, independence, freeness, and so on. If this imperfection degree is finite, then the field degree is just equal to p to the e. So now fix a p-basis, then by definition, an element of the field can be uniquely written in this form, sum over mu, x mu to the p, b mu, where the x mu are elements of the field, and the f mu's sending x to x mu are called the p-coordinate functions, but they are definable. If you have the p-basis, it's a definable function because it's unique. So you have in a field of characteristic p, you have immediately ways of producing new elements which may be highly non-algebraic. Okay. Coordinate functions, good. Now a brief review of the model theory of separably closed fields. So a fact due to Ershoff-Wood. Fix an E which is either a finite number or infinity, then the theory in the language of rings of separately closed fields of characteristic P and degree of imperfection E is complete and stable. And now you are mainly interested in finite E, but I will occasionally come back to infinite. So if E is finite, then you can form the following language, which is more natural. You add constants for a P basis and the coordinate functions as function symbols with respect to these constants, and then you say this theory is SCFPE will be the theory of characteristic P separately closed fields. Degree of imperfection E, Bj form a P-basis, the S mu's do what they should do, so they give us the P coordinates. So, but of course, note I added some structure to the language, to the field, because the constants, the P-bases are maybe, they usually, or they're never definable over the empty set. So I added something, but only constants to the language, because the F mu's are then definable. Okay. So DeLong showed that this theory eliminates quantifiers and imaginaries. But if it eliminates quantifiers, we know immediately that we can, because the field of definition of an ideal is the smallest one, so we can believe that we limit imaginaries because the finitary ones are always eliminated by the trick with symmetric functions, and the rest is then comes from QE. You can also add parametrized or relative p-coordinate functions, which first say if this tuple is p-independent and this element is p-dependent from it, then it gives you the p-coordinate. If you do this, then in any fixed degree of imperfection, you get quantified elimination. Proof is a little bit more complicated. So also in infinite degree of imperfection, you get quantified elimination. But at the level of imaginaries, it's not enough. So because even in finite degree of imperfection, whenever it's not zero, because ACFP eliminates imaginaries, whenever E is strictly positive, in the pure ring language, you do not eliminate imaginaries, and then just if you take an element which is not in k to the p, and you take the coset of k to the p, this imaginary is not eliminated. It's not even interalgebraic with a tuple from the field, so model theorists say it does not even have geometric elimination of imaginaries, where you only care about interalgebraicity. But if you add a p-basis, infinite degree of imperfection, you have elimination of imaginaries, because then it boils down to ideals. Okay. And then something else, namely infinite degree of imperfection, the imaginaries are not classified yet, but there's very interesting work by Martin Hils and Ziegler, recent work, on the equationality of this theory. It is equational, and they reduce the search for all imaginaries within the ones coming from or giving rise to equations, so to say. So maybe there is hope to, with their work, to get to a knowledge, to a complete understanding of the imaginaries. Okay. So that is. I should maybe say that the separately closed fields are the only stable fields, infinite stable fields known, and it's a bold conjecture that they should be the only ones. Okay. But we're not concerned with this today. So now a variant, which is closer in spirit to derivations. So one can also look with a lot of profit in model theory to separately closed fields when one uses Hussey derivations. So what is a Hussey derivation on K? It's a sequence, dn, n in n, of additive maps from K to K, such that the first one is, the 0th one is the identity. You have a generalized Leibniz rule, so dn of xy is this sum, okay, plus L is equal to n to dk of x times dl of y. So it follows from this that for n equal to 1 you have an ordinary derivation, you have the ordinary Leibniz rule there, and there is some iterativity condition. So dm composed with dn is n plus n over n, we choose n, dm plus n. So you see that in characteristic 0 it's not interesting because d1 will give you everything, will determine everything, whereas in characteristic p this is interesting because this guy can be 0 sometimes, and so in particular you get an interesting, you get more, because you know in characteristic p derivations cannot capture so much, and the Hussey derivations can see this, can go beyond that problem. So now assume, for simplicity, that K is of degree of imperfection 1. So we could do finite degree of imperfection in the whole talk, and then we would have to take finitely many stacks of Hussey derivations, which we would require that they commute. And then everything else would be the same, just a little bit more complicated. But all the statements transfer to finite degree of imperfection. Okay, let D be a Hussey derivation on K, then we say that the pair KD is strict if the constants for D1 are exactly given by K to the P. K to the P is always included, but it could be more. So we want equality here. It is called strict. And it's actually easy to see that a separately closed field of imperfection degree 1 can always be expanded to a strict Hussey field. So you choose a P basis B. So what is a P basis in degree of imperfection 1? It's just an element which is not in K to the P. An element from K without K to the P is automatically a P basis. Yeah? If you only have one, choose one. You need to choose one. Then you can find a Hussey derivation which satisfies this. So d1 of B is 1, and dn of B is 0 for every larger n. And there are explicit formulae showing you that it extends to the whole field. You need to write your elements in this P basis and okay, I don't write down the formulas, but there are explicit formulas. So now we have them. We can endow such a field with a Hussey derivation. Okay. Good. Well, I mean, of course, in this example, I said at the beginning, the P basis would be given by T. So we could, for example, work with T and take a derivation which sends T to 1, and the n of T would be 0 for n larger than 1. And there's a unique one. Now, on the model theoretic side, this is good. So if we add to the ring language, instead of adding a P basis, we can add just names for these, or function symbols for the dn's. And then we define SCHP, so separately closed fields with Hussey derivations, as a theory of characteristic P separately closed strict fields of imperfection degree with Hussey derivations. By what I said before, every model of the theory of separately closed fields of degree of imperfection 1 expands to a model of this theory. But this is also, it's a reduct of the one where I name a P basis. Here we do not, if you have the Hussey derivation, you don't see any P basis. It's less information. So it's like it lies between just the ring language and the ring language expanded by B, and where you add a constant B, and somehow in between at the level of definable sets, not at the level of the language. You have this, so it's more canonical. And the good thing is you still have elimination of imaginaries, because by quantified elimination, you can still look at ideals. Of course, ideals when you take the prolongation. So you need to take into account all the dns, but then you are reduced to the same kind of proof of elimination of imaginaries we saw on the other slide. And the theory is complete. Yeah. Okay, so Ziegler showed this 2003. Okay. Also for higher E, yeah, for several commuting partial derivations in higher degree of perfection. Okay. Now, the second brick of our background material are valued fields. So maybe I should be slower here. So some words on notation and conventions. So when what is a valued field? Well, you have a valuation map going from the field to an ordered abelian group, plus an element infinity, which is the value of 0. The others go here. And this gamma of k is called the value group of your valued field. And if you have it, then if you have such a valuation, it satisfies the, you know the axioms, right? V of x times y is v of x plus v of y, and v of x plus y is bigger or equal to the minimum of v of x, v of y, and then the other condition I already used, v of x is infinity if and only if x is 0. So these are the axioms of the valued field, or v is val, yeah, here. Okay, and O is the set of elements of the field of valuation bigger or equal to 0. M is its unique maximal ideal of the set of elements of valuation positive, strictly positive, and the residue field is the quotient of these. And sometimes we just write gamma O M little k instead of k, which we have here, if the field is clear from the context. And because we will work with many sorts, we want a name for the sort of the valued field itself, which is usually called VF of k, valued field of k. So we have this is the main sort or the home sort, you could say. And an important definition. So here I should, here on the slides I don't have enough material, so let me add something. I already said the value group and the residue field are imaginary sorts. These are also imaginary sorts. If you take gln of k modulo gln of O, this is the set which parameterizes the set of A lattices in k to the n, O lattices in k to the n, so O submodules of maximal dimension. Because if you take the standard lattice, its stabilizer is just given by gln of O. And it's also a transitive action by gln of k, so you get exactly all lattices. So this is clearly an imaginary set. It's a definable group modulo a quotient by a definable subgroup. And similar for this one, a bit more complicated. So any lattice is an O module, so you can reduce it modulo the maximal ideal. And it's a free O module of rank n, so if you reduce by the maximal ideal, this guy is a little k vector space of dimension n. But you can take all of them, you take the disjoint union, it's still an imaginary thought. And so it generalizes, actually, the way you should look at it is as higher dimensional analogs of residue field and value group. Because what is the value group? The value group is in one-to-one correspondence with S1. Because what is an O submodule of K? It's just an element of the value group, because you need to name a generator and you take its value, and if you have two generators having the same value, they give rise to the same O submodule, and if they have different values, then it's different. Okay, and the residue field, well, it lies inside Q1 of K, of capital K, because you have the standard lattice, which is just O mod M is containing this union, but you have more, so in higher dimension you get versions of this, which we will see in a second, that basically you need all of them to understand the imaginaries. But so these are called the geometric sorts. These sorts, Sn and Tn.
Can you prove that they're not definable?
One can prove, yes, one can prove. So, on the next slide, you will see the results. So Haskell, Ruszowski, McPherson, first of all, they showed that they will be enough in algebraic closed valued fields. And they also proved that, and now I'm not sure about the complete, you certainly need all of the SNs. And I think you also need, all, cofinitely many, of course. The larger SNs can always encode the smaller ones. But finitely many are not enough. And there's also a result about the TNs, but I think you essentially need all of them, and one can prove it. I will give an argument, there's a simple argument why the residue field, for example, is not encoded in the valued field, just to see how one can do this. Yeah. But we will come to this in a second. So now I need to talk about language. This is a little bit, should not frighten you, it's just I need to introduce languages now. So we will look at two languages. There's also one sorted language where you just have the valued field, and you add a binary relation for x divides y for v of x is smaller or equal to v of y. I will not talk about this language here. And there is a natural language with three sorts. So for the valued field, for the residue field, and for the value group, that is this one. So L gamma k, we have these three sorts. So somehow as the main players in a valued field, the valued field itself, residue field, the value group. And so you put the ring language on the valued field, you put another copy of the ring language on the residue field, and you put the language of ordered abelian groups on the value group, and then you connect the sorts. Well, one map is obvious, the evaluation map from the field to the value group, and there is, for some technical reasons we will see in a second, you add a binary res map. So it takes a pair of elements of the valued field and it goes to the residue field. It's defined as this. Capital res of x, y is the residue of x divided by y, if this makes sense. So if x divided by y is an element of O, you take its residue, and else you define it with 0. You will need this for quantification in a second. And then there is another language which takes all the sorts, the geometric sorts, so this one, and I call it LG, and I will not make it explicit. It's not interesting to see exactly how this goes, but there is a language extending this language in three sorts, but it has more sorts, so it has these three, and then the lattice sorts and the reductions of the lattice sorts as well, with obvious maps between them. Of course, you have a map going from GLN to SN and so on. And you have a precise syntax is not important. Okay. Now, the model theory of ACVF. So, ACVF denotes the theory of non-trivially valued algebraically closed fields. And already Robinson, he basically proved this. He proved model completeness, actually, but from his proof one can infer such results. So, in the 50s already, this theory eliminates quantifiers, for example, in the three-sorted language I gave. And its completions are given by fixing the characteristic of the valued field and the residue characteristic. So you have one complete such theory in characteristic 0, 0, one in 0p. For example, CP is a model in characteristic 0p, and in PP you also have one complete. Okay. So that is starting point. So it's a model companion of the theory, or the model completion of the theory of valued fields. So everything which there's a notion of Nullstellensatz if you want, phrased properly in these terms, whenever something quantifier 3 is true in a larger valued field, then it's already true in this one. Good. So this is the start, but now the important corollaries on somehow the geography of these sets which are around. So in any algebraically closed non-trivially valued field, we know that the residue field is algebraically closed, and the value group is a non-trivial divisible ordered abelian group. Right? And actually, both are pure. So in this structure where you have parameters from everywhere and formulas which can talk about the three sorts, still on the residue field you can only see what already the field in the residue field can see, namely the constructible set. Since it's an algebraically closed field, the only definable sets are the constructible sets, but even in the larger structure you only get these, and similarly in the value group you only get semilinear sets. So sets described by Boolean combinations of inequations with integer coefficients. Nice. So gamma is O minimum, little k is stable. I mean, and the whole game is, and the game of model theory of valued fields is always, of Henselian valued fields is always to reduce the study to little k and gamma, always. Yeah? So that is, here little k and gamma are particularly nice, so that's why the theory is so nice. Okay, and here's the important fact, which somehow is the key to, I mean, we are generalizing this fact in what I will, or this theorem, yeah? It's a big theorem, a very important theorem from 2006, which it was proved much earlier, but it's published 2006. Any completion of ACVF eliminates imaginaries and quantifiers. That is not important, but depending on the choice of the language, any completion eliminates imaginaries in the language with geometric sorts. So these are the only imaginaries we have to add, and all other imaginaries can be embedded definably into a finite product of these sorts. I mean, you have, what does it mean? If you have an imaginary sort, even in ACVF, there is an n, so that you can embed it into k to the n, which is VF, yeah? And usually it would be finite product, but you can encode Sn1 cross Sn2 and so on. You can find in the sum of the lattice sort, so you can, it reduces every limit. So every definable quotient is a subset of this. It's a very strong theorem. It's a classification of definable quotients. There is a very nice proof by Will Johnson, which is not this one, but which is based on an original proof or another proof by Warshawski. You can prove this in 2 or 3 hours to an audience which knows a little bit what's going on. But nevertheless, it's a super important theorem because it started somehow, and also the work to prove this started what is called geometric model theory in valued fields. Because before, somehow, stability theory could not really be used in valued fields. And after this, one could use more and more, and until this day, somehow the use of stability theory and related things in the valued context relies on this work somehow. Okay, and one may, this answers Gleb's question, so one may show that essentially one needs all sorts from G to eliminate. Now I will not show this, but let me show why you need, for example, the residue field. So why can't you definably inject the residue field in the field? Okay, there are several arguments. It would also follow from quantified elimination, but I don't want to give that proof. Another proof is, well, if it did, I mean, you can find a model in every completion, so in any characteristic, you can find a model of ACVF which has countable residue field, but which is itself uncountable. For example, CP in characteristic 0p, it is a cardinality continuum, and the residue field is FP bar. You have similar models in other characteristic pairs, and at the same time, we know that a definable subset, by quantified elimination, a definable subset of a valued field, if it is infinite, it contains an open. But open sets have the same cardinality as the field itself. And so we may choose, and in one variable, then it's also true in n variables. Yeah? So every definable set in n variables, if it is infinite, it is the same cardinality as the field. But we find fields which are uncountable themselves. So every definable set of k to the m, if it is infinite, it's uncountable, but the residue is countable, contradiction. Same for the value. Same for the value group, because here, for example, the value group is q, cannot embed q. And then for the SNs and for the TNs, it gets more complicated. So this analysis is not enough, but I mean, it shows at least.
Is it still a cardinality analysis?
For the SNs, you can still do, yeah. But then to show that it is not enough to have little k and gamma, I mean, for example, you cannot encode all the balls, and then it gets more complicated. Yeah. For the lattices that they cannot be embedded is.
Oh, I see. Yeah.
That
Okay.
is easy. But, okay. Right. Okay. So this result boosted a lot of work in the area. So what about classification of imaginaries in other valued fields? So similar In the following enriched valued fields, or just valued fields, the imaginaries are also shown to be classified by these geometric sorts, so SNs, TNs added. Real closed valued fields with a convex valuation. You take your favorite, for example, take QZ series and take the valuation given by where the finite elements are the valuation ring. Then it's a model of ACVF, and they have the same kind of, they display the same classification. Harder and maybe more interesting is it's true in the p-adics, you don't even need the Tn's because the residue field is finite, but you only need the SNs there. And ultra products of p-adics. So this is by work of Rochowski, Martin Hils, was used to generalize the Neff style rationality results to imaginary counting. So yeah, it's more difficult because because the value group is discrete. Like the analysis for balls, it gets much more involved in p-adics. And then there is also this theory, the VDF I talked about, the Scanlon's, the model companion of the theory of valued fields in equal characteristic 0 with a contractive derivation. It has also the dimensional imaginaries. So Sylvain Rideau proved this. Cute argument, and actually what I present follows these ideas. Right. So now to the topic of to our own work. So I have until past, right? Okay. So now we merge the two. So we have seen the model theory of separately closed fields is nice. We have different ways to approach it, either with p-basis or with fuzzy derivations, and then we have seen algebraic closed valued fields. And the two marry, they merge in the nicest possible way. So no strange new phenomenon appears in some sense, in a very strong sense. Okay. Good. Let's see. So first, the theory of separately closed non-trivially valued fields of characteristic P is denoted by ACVF P. There is a little observation, but I want to prove it because it's essential. It's easy but essential. It's that if you have a separately closed valued field, non-trivially valued field, then itself, or k to the p to the n, even is dense in k bar in the algebraic closure. Dense in the sense of the valuation topology. And if the field is it's omega saturated, then this holds even for kp infinity. But this is then by compactness. Yeah, so k is dense in k bar, or k to the p to the n is dense in k bar. What do we have to show? Look, k bar is just the union of k to the p to the minus n, because it's the perfect closure of the field. And so by induction, because I'm dense in k bar, even only if I'm dense in all of these, by induction, it's enough to show that k to the p is dense in k. Then I can shift, I do it finitely many times, and k to the p to the n will be dense in k to the p to the minus m, and so on. So I only have to show that k to the p is dense in k, for the whole statement. So by this, let's check. So what does it mean to be dense? I mean, the topology, the valuation topology is given by the balls. Let's look at this open ball of elements B, K, where the valuation of B minus A is bigger than gamma. This is a typical open set in the field K. I have to find a point from K to the P in it. Good. Okay, what can we, it's easy. I said it's an easy proof. So we choose an epsilon from the non-zero element epsilon with large enough valuation, so with valuation larger than the maximum of gamma and the valuation of A. Since K is separably closed, I will find a B which satisfies this, because the polynomial x to the p plus epsilon x minus A is separable, so I find a solution. That's one. And then one shows easily, looking at that there cannot be cancellation, that B must be in O, and then the value of b to the p minus a is the value because this is 0, so this is equal to the value of epsilon b, and by the choice, this is bigger than gamma. Easy. Good, and if a is not in O, well, then you use the homotopy and you strengthen a little bit this condition, and you do basically the same thing. So I don't like this, I don't show. Okay, so it's dense, good. And then a second lemma, if you have a dense subfield, wherever it comes from, you have a dense subfield of a valued field, then it has the same lattice sort points and the same reductions. I'm going to prove this here. So why do we have the same lattice sort? Well, GLN of O is open. Is here open? In GLN of K. So is any multiplicative translate. And so I always find, since K to the P is dense, since K is dense in K bar, yeah. So, sorry, here. Yeah. As K is dense in K bar, there is M prime in GLN of K with M prime GLN of O equal to M GLN of O. So I can represent my lattice with a matrix from with coordinates in K. Okay, this is for the essence. Yeah, so plus, I mean, this is true for I prove it for K and K bar, but actually it's just if K is dense in L, that's the same lattice points. And now for the TNs, okay, for the TNs, it is enough to do it for the standard lattice. Because since every lattice is represented by a matrix over the smaller field, I can just choose a basis and work there. So enough to show for Tn. Now I go to that setting, Tn of L equals to Tn of K. Enough to show that that O to the n modulo m to the n, or the standard lattice of L somehow is equal to O to the n mod m to the n of K. So that I have the same reduction of the standard lattice, because I can choose the basis. But this is clear because every coset of m to the n is open, so it must contain someone. Okay, since a plus n to the n is the open. So we're done. So if you are dense in a larger field, you have the same geometric sorts, in particular the same residue field, the same value group. It means that the extension of the valuation is immediate, by definition. But it's true. So all sorts do not change except the valued field sort itself, but all the imaginary sorts keep the same. Good. Now, several contexts to look at ACVF, P. First one with P coordinate functions. So here the classification result was given first. As I said, it's the Hasse derivations lie below. So if I have a P basis named, I have more structure, so it is easier to classify imaginaries. And we will see that it's easier. Okay, so let L tilde be either the three-sorted language I explained, or the geometric language I did not explain, but in which we have quantified elimination in ACVF. That is the crucial point. Essentially, Delon proved that the completions of this theory are given by specifying the imperfection degree, as was the case without valuation, and that it has quantified elimination if you add relative P coordinate functions. Now, this context is less interesting for us, but so the second one, for finite E, remember that STFPE was when I added names for a P basis and the P coordinate function, so let's do it, plus the separably closed valued field theory as well. This has quantified elimination also. follows from 1. It's a specialization of 1 in some sense. You only need these coordinate functions for this p basis and not for all. Okay. And first, together with Moshe Kamensky and Sylvain Rideau, we proved that in this language we have elimination of imaginaries in the geometric sorts. So this is not the proof I want to closer present. I just want to give you the rough ideas, because it's harder with Hasse derivations. So somehow reducing and forgetting this p basis and working only with the Hasse derivations makes things harder. And since the small is tiny, the step is tiny, one could also say, why do we this? But we somehow it's also we learned something when we did it, and we got many others with. But the results I will talk about in the model theory seminar actually, but I cannot talk about here. But somehow, yeah, because one has also the intuition of derivations, because one has them. Yeah, good. Okay, so how does the proof of this go? Roughly, very roughly. It's topological reduction to ACVF, and this density plays a big role, because we have the result by Haskell, Olszewski, McPherson that the imaginaries are classified by these geometric sorts in ACVF, and we want to push it there. So if you name a p-basis, there is this nice observation. If you write your element in the p-basis, in one way, it's not at all a function which is rational in the sense of field, but backwards it is. So in this direction, it's really functions which are nasty, but backwards they are rational functions. So you can, if you make this explicit, you take quantifier free definable set. Sorry, this is bad. Quantifier free without I should say semi-algebraic here. So this is wrong here. It's not enough. It should be semi-algebraic. So every definable set using the p-basis and using the f mu's, or the p-coordinate functions, you can make their use explicit up to going to higher arity. You are in definable bijection with a semi-algebraic, I should have written, so without the p component. So it should be x is in zero definable bijection. This uses the p-coordinate functions and so on, with y, and y is semi-algebraic. So it's definable in a quantifier-free manner only in the language of value fields. Okay, it's easy. So this one, first step. So when it comes to, we have to code definable sets. Up for coding, doesn't matter if I'm in zero definable bijection, the same automorphisms of the structure will preserve me and the other ones, so we can work with y. We have to code y, same thing. And how do we do this? So it's a semi algebraic set, so given by inequalities on polynomial values of polynomials, and we can stratify the situation and use the V density of it. Okay, the density I expressed it in K. A K is dense in K bar. But a little argument shows that for every irreducible variety defined over K, the K points are also dense in the valuation topology in the K bar points. It's even true in much greater generality, but separately closed fields, it's rather easy to see. And then we stratify, take V closures, so we manipulate a little bit the situation so that we end up with a situation where this Y, this set, is actually itself dense in the set of points I get when I use the same formula, but I evaluate it in the algebraic closure. This formula is not talking about a variety, it's a semi-algebraic set, so they're unequal. But you can reduce to this situation where the K points of, when you evaluate the formula in K, it is dense in the K bar points. And then in this way you get access to the code. You get access, somehow you can see what happens in the algebraic closure from the point of view of K. But in K bar you have a code because ACVF does eliminate imaginaries, and somehow you manage to see this code already from the point of view of ACVF, and you can use it. Okay, that's very rough, but I want to now present the same kind of proof, but which gets more involved with Hasse derivation. So let's look at this. So now we merge the second part of the separably closed world, so with Hasse derivations. To take the valued side, nothing changes, but here we take Separably closed Hasse fields, degree of imperfection 1. And the language is now the language of valued fields we had, and we add all the dns. So it could be either L gamma k or it could be LG. Doesn't matter. But on top of it, the only operators we need are the dns. No constants. So it's a reduct of the other language. A reduct in the definitional sense. So first we showed, I should say before, yeah. The other theory is not complete, because if you name a p-basis, it depends on the valued field type of the p-basis now. Before, in the field case, without valuation, a p-basis is necessarily algebraically independent, and there is only one choice of p-basis from the point of view of types. In the valued setting, it depends, because you can take a p-basis which lives entirely in the maximal ideal, you can take another one, whatever. So it's no longer complete, but this theory is still complete. We use a little trick due to Ziegler to see this. And it has quantified elimination. Good. Now, if I give a name to the imaginary geometric sorts, as a properly imaginary sorts, it means those geometric sorts which are not equal to VF. And what I have explained, they have the same k points, same k bar points. So this is somehow, at this level, we cannot distinguish between the algebraic closure and the field itself. And even Kp infinity has the same points. If you work in an omega saturated model, even the smaller model of ACVF also has the same imaginary points. So you can also think of an infinitesimal thickening of that one. Only at the level of the valued field you see it. At all the other sorts, you get the same points. So GM. And actually, the induced structure is the same with both classes. So you can either look at it from the point of view of K bar, it's in ACVF, or you can look at it with the classes of SCVH, so from the point of view of K, and it gets the same induced structure. Of course, in one direction it's clear, so you always have at least this structure here, but the other way follows from quantified elimination. Okay. In particular, because they are both living inside GM, on little k and on gamma, nothing new happens. So little k is still a pure algebraic closed field in calculus dp with no new structure. Gamma is still a pure divisible ordered abelian group with no new structure in this context. Okay. And now, somehow the stronger theorem, which implies theorem A, is that even in this context, we have elimination of imaginaries in these sorts. Actually, we first had the other proof, but then Sylvain joined, and he brought his idea. He brought this idea of from BDF, from the theory of by Scanlon I talked about, and we could merge and we could give this maybe more conceptual proof, but which is no longer topological reduction with Hasse derivations. So proof strategy. As I said, so we follow somehow the ideas of Sylvain Rideau, which in some sense is also a reduction to ACVF, but using prolongations. So you by quantified elimination, we know that you can understand a type if you understand the ACVF type of the prolongation, because you need to, if you have a tuple, you need to take all the dns, you apply it, and you need to know where they lie with respect to value conditions. But then you have to transfer it to a proof of elimination of imaginaries. And here's the main lemma. And so, so I want to make a little bit of publicity for the later talk in the model theory seminar. So basically, I will explain in a lot of detail how one can obtain this result. This is our main lemma. So what does it say? So here, there are some things I have not defined, so we go carefully through this. It is also at the heart of Will Johnson's proof for the elimination of imaginaries in ACVF, so it's like philosophically the right thing one should prove. And there is even a stable counterpart, which is due to whom? I don't know, Lasker. What is that? So that is enough to have canonical basis to have weak elimination. I don't know what this is called, who proved this exactly, but it's exact analogon. For those who know stable theories, if you know that canonical basis of types of the models are real, then you have already weak elimination. It's the same here. So what do we have? Take our model, take a non-empty definable set with parameters, so k definable, of k to the n. It's enough to look, actually it's enough to look at subsets which live in in the valued field, so VF to the n. You don't need to look at definable subsets of the other sorts. It's enough in the home sort. And now this is a bit complicated set. So what I told you, there is this construction by Schellach of adding all imaginary sorts. In this, if I add all the imaginary sorts, I have a code. I told you, so it eliminates imaginary. So I take this code in this world with all imaginaries, and I take the algebraic closure there. What is the algebraic closure? It means it is solutions of formulas with finitely many solutions with parameters there. Or equivalently, elements which have finite orbit under the automorphism group in a sufficiently saturated mode. I do this, but in this imaginary world. But this imaginary world, of course, it includes G, because G's are imaginary. And then I only take the G points. So I take the G points. So I only take those points which I think will be enough to have elimination of imaginaries. So they are all imaginaries, we take the points there where we think it's enough. So if everything is okay, it will be enough. Yeah? So we take this set A, which is algebraically closed in G by construction. And then there is an A-definable type which says I'm in X. What is an A-definable? Maybe you don't all know what a definable type is. No? Let me explain it. A type, a complete type is so if you have P of X, say in Sn of K, for example. X is a tuple and n tuple. So it can. So you have a formula phi of x bar y without parameters. A formula. Of course, given a bar, let's say b bar in k to the m, where m is the length of y, then you for every tuple b bar you have to decide if yes or no. You put it in the. So you have an instance. And you need to know, is this instant init or not? And the type is called definable if this decision on B is a definable condition. And it's called A-definable if the formula you need to make this decision R over A. It's A-definable if there are formulas with parameters from A, say theta phi of only in the parameters, such that you have phi of x, y is in P, if and only if theta phi of B holds.
B in decision.
B, yes. So, yeah, okay, good. In stable theories, all types are definable. But here we are not stable, and the density of definable type also we restricted to parameters. Yeah, so if we took all in the stable theory, it would always be true. But anyway, so this is the main point. If we have this, so from here to the result, it's not far, because by general nonsense, if you have the density of definable types and you have coding of finite sets, which I will explain, you get elimination of imaginaries, because this is what is called weak elimination, and one knows from weak to strong there is only needed to code finite sets. So this is the heart, and I will not explain how I prove it, or how we prove it, but okay. So for the rest, it's easy. You remember I showed in the beginning that I didn't show that all finite sets in fields are coded, but I did an example. You can believe with symmetric functions you get only go finite tuples. And here the same, but here we reduce it to ACVF. So some observations. If you have an automorphism of separately closed valued field, it lifts to an automorphism of the algebraic closure, even uniquely. It's a perfect closure, so just a unique way of lifting it. In particular, you have an information on a definable closure. If you have two tuples, which live in the geometric sorts and are k points, and if B is definable over A bar in the algebraic closure, then it is also definable in the separable closure, because it goes the other way around, and you can lift automorphisms. By automorphism characterization of definable closure, this is obvious. Secondly, whenever you have a tuple from G of k bar, there's another tuple from G of k, which is interdefinable in ACVF. Why this? You have to look at, first of all, in the purely imaginary sorts, in the sense T and little k gamma, there are no new points, nothing to do. Now you take a field element. If you take an element of a valued field, little a, in k bar, you can raise it to a certain pth power, k to the x to the p to the n, so that it falls into the field. But the two are interdefinable because there's a unique p to the n through. So that's why you can also do field elements. So that is somehow easy observation, but you put everything together, you can code finite sets. If you have a finite subset of G of k, first of all, it can be coded in ACVF by a tuple in G of k bar, but this one is then interdefinable in ACVF to a tuple from G of k, but this interdefinability is even more so true in ACVF. So you get coding of finite sets. You get coding of finite sets almost for free, reducing it to coding of finite sets in ACVF. And so the big part which is missing is this density of definable sets. I want to say a couple of words what are the proof ingredients. As often in model theory, even if you are not interested in pairs, pairs are good. I mean, this is true from the start. Say, I mean, even if you prove Morley's theorem, for example, you work with pairs, or if you, I mean, many things early on with pairs, but here it's particularly true. So what you study, you want to do a transfer from k to k bar. Of course, an obvious way to do it is you study the structure in which both coexist. But it could be too complicated. But actually, one can understand this structure. So you take the structure which has k bar, and then it has a predicate for the subset k, and in the valid field side, you only need it there. And what do? You put on the predicate, so on k, you put the full, so you put the geometric language, but you also put the, on k, wrong way, yeah, on k, sorry, yes. So the little one is the model of ACVH, and you put the geometric language on k bar, and the geometric language, including the Hasse derivations, on the predicate. So everything you have, you put it, plus a predicate, you name by a predicate the little field. And the point is, one can understand this theory, and here the density plays a role. This is the first step. The second one is we use prolongations. So you start with your definable set, but actually you don't like it. You take the prolongation of it. So you take it's a pro-definable set now. The image under this sequence of maps, Dn, and that's another. It's a pro-definable set, and this one. Somehow in this, it is enough to exhibit an ACVF definable type in that one, because it has already understood how the dn's go, and now the problem remaining problem is an ACVF problem. Okay. And that's why we can. Okay, we know already that definable types are dense in ACVF. This is part of Johnson's proof, for example. That's also, you can just show it, and. One can move up and say, okay, even in such pro-definable sets, we will find ACVF types which are consistent with such a definable set. But at the cost of having a definable scheme in the pair language. So the language will be the wrong one, and the parameters will be the wrong one, because we worked in a complicated structure, and then we need some magic. And Rideau and Simon provide this magic because it is already used in his proof of VDF. So this theory of the pair, it has a particularly nice model. It has a model in which the value group is the group, ordered abelian group of the reals, and the valued field, so the larger one, the left one, yeah, the bigger one, is maximally valued, meaning it does not have any proper immediate extension. It's also called spherically complete, so every intersection of balls, I mean, every nested family of balls has a non-empty intersection, sorry. This is fairly complete. And there are such models. And if there are such models, these models, they fit nicely in every elementary overstructure. They are what is called stable embedded in every nice elementary overstructure. And in that, okay, applying some techniques, one can then descend the parameters to the ones one is interested in. Okay. Good. Yeah, so I think I'll stop here.
Questions? So what's the reducer model?
Okay, so it says, when you have an NIP theory, okay, it says almost what I wrote. It says if you have T and then you have an expansion T tilde. T is NIP. And they have a model of T, okay. So the assumptions, yeah. There exists a model, whatever, a very nice model, so that this very nice model, T star, so T star is T tilde. Such that the reduct, so if you forget M, so you reduce to some other language L, is now it comes a technical, is uniformly stably embedded in any overstructure. What is this? N. So it means whenever you take a definable set with parameters from N, you intersect it with M, you can rewrite it as an M-definable set. But even better so, if you vary your parameters in a family, there's a single formula which somehow allows to describe the intersection of the trace of a definable set with parameters from N in M can be uniformly written as an M-definable set. And this is the case for, models of ACVF which are maximally complete and have the value group equal to the reals. Actually, for the reals, it's, minimal theory is very involved, right? So this is, on the value group side, everything is fine, but in addition, by metastability, you know that already the types are defined, there are only definable types then, because in the value group there is no problem, and on top of that, everything is definable anyway, but then for uniformity, one has to work a little bit, but it's true. And so, but how is this proved? I cannot phrase it. It's somehow some variation on honest definition. They call it external separability, but it's like a little variation on honest definitions. So.
But in this statement, what is an assumption and what is the conclusion?
Then. Like only assumptions. There's only assumptions. Then. Now, then exactly what I want. Then any M tilde invariant or M tilde definable. I should rather write L tilde of N to make clear that I mean this global type, so over the monster model, yeah. P tilde, the reduct of any, so for any, the type P, which is P tilde is equal to L, or L of U if you want, is L invariant or defined. So somehow you can go down to this. I mean, maybe so this is really in VDF. It's the same thing. You prove something in VDF, but actually you want to have it in ACVF. But since there are nice models, I mean, these maximally valued models with nice value group, you have this channel phenomenon, and it's very powerful actually. I mean, it was designed for the VDF case, but it uses really an IP, so I cannot explain it here. It uses heavily the NIP assumption. But so this is, I mean, in some sense, the topological reduction is a much softer proof than this one, but but we can use this stuff to do other things as well.
Questions? Das heißt, again?